Okay, guys, let's talk about cardiac electrophysiology. Um, uh, this topic can go so deep, so I'm really just going to brush the surface on it here and talk about kind of what I know about it. But, this is a subspecialty of cardiology, so you can go as far as you want and as deep as you want with this, but hopefully this will be helpful for you guys to understand the kind of electrical system and what's going on in the heart. So, as with any kind of the electrical systems in the heart, right? They're driven by action potentials, just like the action potentials in your nervous system. And the heart has two different types of action potentials, right? They have a pacemaker action potential and a non-pacemaker action potential. Now, the pacemaker action potentials are responsible for all of the automaticity. They generate the impulse that causes the depolarization, and they do that spontaneously. So those are the cells of the cardiac conduction system. Now, the non-pacemaker cells are the cardiac myocytes, so the muscle of the heart, the cells that are actually getting stimulated to contract and then squeeze that blood out and get it around the body. So, what do we know about pacemaker cells? Well, cells. The first thing that you should always remember is that they are spontaneous, right? So they happen on their own at a set rate. Okay, you don't need an input to make them to make the action potential fire. The next thing that you should know is that they're mainly controlled by the sympathetic nervous system and the parasympathetic nervous system, right? And that's through different GPCRs and receptors that we'll go over a little bit later. As far as non-pacemaker cells go, what's important about these is, well, they're not spontaneous, right? And since they're not spontaneous, they need an input to have that action potential to cause contraction. So where do they get that input from? Well, they get that input from the pacemaker cells. Right? So that's kind of like the basics of those two types of cells. Now, we're going to talk about the actual action potentials, and they look very, very different. So you can see this is the action potential for a pacemaker cell, and this is a non-pacemaker cell, right? And as you can see, just by the shape alone, you're like, well, they must be very different. One is a hill, and then one is some weird type of slope thing that I don't even know what the technical name is. So, why are they like that, okay? Well, they're like that because they have different currents that are happening, different ion currents that are flowing across their membranes that are controlling these action potentials, right? Just like the flow of ions across a nervous cell is responsible for, transmitting the action potential in the nervous system, the same thing holds true with the cardiac pacemaker cells and non-pacemaker cells, right? But the action potentials look different. And that's because there's different phases. And in the different phases, different ions are doing different things. So as you can see, the pacemaker action potential only has three phases: a phase 0, a phase 4, and a phase 3, right? And a non-pacemaker cell has four different phases, right? So they have a phase 0, a phase 1, or excuse me, 5. A phase 0, a phase 1, a phase 2, a phase 3, and a phase 4, right? And they kept it like this so the numbers would generally correlate to what's going on in that action potential, but there are some important differences between like a phase 4 and a pacemaker and a phase 4 and a non-pacemaker, or a phase 0 and a pacemaker and a phase 0 and a non-pacemaker. So let's go over those differences. Okay, so we'll start with 0, right? We'll start right here with 0. Phase 4 is always going to be our resting potential, right? And phase 0 is going to be our depolarization phase. So as you can see, this is kind of a gently upsloping line. It's not, shooting up like a rocket, okay? And what is causing that is a strong inward current of calcium, right? So we're coming here, we got a strong inward current of calcium, Ca2 plus. So strong inward flow of calcium. Okay, and that causes depolarization, but a gradual depolarization. Next, we have this transition, right? So what's happening there? Okay, well, the calcium stops coming in, right? So those calcium channels close, and then potassium starts to move out of the cell, right? So we have from here, this way, we have K plus out. So we'll say K plus out of cell, and Ca2 plus stops into the cell, stops going in. Okay, great. So what's that causing, right? So since the calcium's not coming in and now the potassium's going out, you're having a gradual repolarization, right? And then that's going to get us down to 4, which is our resting potential. And this is the most important difference between, these two things. Obviously, there are other differences, but this one is really important. So in phase 4 of the pacemaker action potential, we have sodium coming into the cell, right? But it's through something called a funny channel, right? And why is it called a funny channel? Because it opens when it's hyperpolarized, and it causes a slow leak of sodium into the cell, right? So it's a slow leak. And it causes instability of the resting potential. So that equals instability of the resting potential. And that instability is what actually causes the heart rate, right? That's what causes the automaticity, is these funny channels, the sodium's leaking in, and it opens when it's hyperpolarized, and then it moves up, and then it hits a threshold. And then once it hits threshold, that's when the calcium channels open up, and then you get the rest of the action, or the rest of the pacemaker potential. Okay, so that's the pacemaker potential. What about the non-pacemaker potential? All right, well, let's talk about that. So we'll start off with phase 0. And again, this is depolarization, right? But this is going to be rapid depolarization. Very similar to a neuronal action potential. So we have the fast sodium channels open up, and all the sodium comes rushing in. Fast Na plus open, Na plus in. Okay, so boom, they open. All right, well then what happens in phase 1? Well, fast sodium channels close, and then potassium starts flowing out of the cell. So K plus out of the cell, right? So we have, right from here to here, we have Na in, then from here, kind of all the way out to here, we have K plus out. All right, next we have phase 2. So phase 2, calcium is moving into the cells, right? So Ca plus into cells. And this is important because it's counterbalancing the potassium that's coming out, right? So the charge is remaining neutral because they're kind of trading charge for charge, and that creates the plateau, right? So K plus is still going out, and then that gives you the plateau. And that kind of is what drags that out. Next, we have phase 3. So phase 3 is the Ca plus close. The calcium channels close, so Ca plus stops going in. Okay, great. Well, what does that mean? Well, the potassium's still going out, so what you're going to have is repolarization. So this equals repolarization. And then in phase 4, that's going to be your resting membrane potential. Resting membrane potential. So potassium is going to reach equilibrium, and then the sodium and the potassium kind of reaches that equal in, equal out until it's resting, until it gets the next impulse to fire, and then boom, those sodium channels open up and the cycle starts over again. All right, so that's kind of what's going on from an action potential electrical kind of side. So let's talk about conduction velocities real quick. So there's two places where you want to know about conduction velocity, and that's the SA node, or where it's the fastest and where it's the slowest. So the SA node is where it starts, right? So that's where this pacemaker potential, is creating the heart rate, right? That instability is creating that, firing of the pacemaker cells that's causing the heart to contract, and then it keeps doing that, and that's what establishes the heart rate. So where is that conduction going to be the fastest? Well, that's going to be the AV node. And if you remember from our internal cardiac video, we were saying the AV node is responsible for slowing down the conduction from the atria to the ventricles, allowing for that excitation contraction coupling to happen so that you can have these non-pacemaker cells go through a full contraction cycle, relax, and have time to get out of the refractory period where they wouldn't be able to contract again with the stimulus, and be ready for the next time that pacemaker cell fires out another hit. So excuse me, so this is the slowest. This goes here, sorry. And the fastest is going to be the Purkinje system. So it's spreading out from the bottom, and it's getting to all of the non-pacemaker cardiac myocytes, right? It's getting all of those to contract and then contract at the same time. So what is that refractory period I was talking about, right? That we were, in relation to the AV node. Well, the refractory period is the period of time where the myocytes, or the non-pacemaker cells, can't depolarize. All right, and so there's 3 different types. There's the absolute, effective, and relative. So the absolute is no signal, no matter how big, can cause depolarization. All right, so no matter what happens, no matter how big the signal is, the absolute refractory period is the cardiac myocyte will not respond to it. Then there's the effective refractory period. So what the effective refractory period means is that, the cardiac myocyte, if a large enough signal or a large enough stimulation, so large stim, it can generate an action potential, right? But it cannot propagate. So it would just be stuck to that one cell, right? It wouldn't have the ability to move that signal forward. And then what's the relative refractory period? Well, if you can see kind of the trend line coming here, it's a large stimulation can generate an action potential, and it can propagate. Okay? So that's what you need to know about the refractory periods. And so now let's talk about this cardiac excitation contraction coupling. So all of these, this, non-pacemaker action potential impulse, it comes in, and how does that cause the heart to contract? How does it affect contractility? All that kind of stuff, right? So you have your action potential. It's coming down. It's coming in here, swoop, and it comes on in, right? And it hits this little receptor right here. Now this is an L-type calcium receptor. And what that is going to do is once that action potential hits, it's going to allow calcium to flow into the cardiac myocyte. Now, the calcium is then going to act directly on this receptor right here, which is the rhinitidine receptor. Now, the rhinitidine receptor is part of what is this box right here, which is the sarcoplasmic reticulum, right? So let's say this is the SR. And inside the SR, we have a bunch of calcium, right? It's all stored up in here. And the amount of calcium in the sarcoplasmic reticulum is directly correlated to how strong your contraction is going to be. So when the L-type calcium channel gets the action potential, opens the rhinitidine receptor, then you have this calcium all flowing out, right? So it flows out of the sarcoplasmic reticulum, and then what's it going to do? Okay? Well, then this calcium is going to go down, and it's going to bind this little molecule, right? So this is the actin-myosin cross-linking, my crummy depiction of it. And this little ball right here that I kind of drew dark shaded is supposed to be troponin C. So troponin C is the troponin that binds calcium, right? And why is that important? Well, in order for cardiac smooth muscle to contract, calcium has to bind troponin C. Then what happens is troponin C causes a conformational change, and troponin T, which is bound to troponin C, is also bound to tropomyosin. Right? That causes a conformational change, right? So this band of tropomyosin is covering the actin, the binding sites, right? So we need to expose that so then they can bind and you can have cross-bridging and then contraction can happen, okay? But in order for that to move, troponin needs to be bound to calcium, causing a conformational change which moves tropomyosin out of the way of that actin-myosin binding site so it can allow cross-bridging. So, calcium binds, tropomyosin moves out of the way, allows contraction to happen, contraction happens, right? So, say tropomyosin covers actin-myosin binding site. Okay, and then troponin I just threw it in there. Troponin, troponin I is what makes the conformational change. And troponin I, if you guys have ever heard of getting a troponin for signs of cardiac ischemia, that's what we're getting. We're measuring the level of troponin I, right? Because it's only found in cardiac muscle, right? So if it's free in the circulation and it's high, we know that cardiac muscle has been damaged because it's the only place in the body where it comes from. Okay, so that's how we get the contraction. There is a couple other ways that we can mess with the calcium content in the sarcoplasmic reticulum. So over here we have a beta-1 receptor, right? And a beta-1 receptor is a GPCR, right? So that's the 7 or 8, I don't know, I forget. It's a 7-bound intramembrane protein, and that is innervated by the sympathetic nervous system, right? So sympathetic nervous system comes in, stimulates the beta-1 receptor. Beta-1 receptor is going to activate its GPCR, What that's going to do is it's going to increase CAMP via adenylene cyclase, right? And then that increased CAMP is going to go ahead and activate or increase protein kinase A, right? So increases pKa. Now, pKa acts on two separate things in regards to calcium. The first thing it does is it's going to come down here and it's going to phosphorylate this, and this is just a calcium channel. So it's going to allow more calcium in. So more calcium equals more contraction, right? So you're going to increase your contractility. You're going to increase the power of that squeeze because you're allowing more calcium in, which makes sense. If you have, if you're trying to run from a bear, you probably need more cardiac output. So you're probably going to need more calcium in there, and that's going to take care of that. Now it also does something else. Protein kinase A is going to come all the way over here, and it's going to phosphorylate this little guy. So beep, phosphorylates that guy. Now, this is called phospholambam, and we've talked about contraction, but how does contraction stop, right? Well, you have to get rid of the calcium. You have to get the calcium back into the sarcoplasmic reticulum, or else everything would just stay contracted, right? But we need to relax so that we can have another contraction cycle and our heart can beat, right? Our heart can squeeze. So as the calcium dissociates off of troponin C, right? So we'll say Ca2 plus comes off. It's going to be pumped back into the sarcoplasmic reticulum by this pump, CIRCA, right? And it is an ATP pump, right? So it requires energy. So that's what gets this calcium back into the sarcoplasmic reticulum. Now, the reason that this little guy is important is its name is phospholambam, right? And phospholambam is an inhibitor. So when phospholambam is bound and unphosphorylated on the CIRCA protein, it inhibits the CIRCA protein, right? So you can't use that CIRCA ATPase. You're not pumping calcium back into the sarcoplasmic reticulum, and you're not getting cardiac relaxation. So what happens when pKa phosphorylates phospholambam is you turn off the inhibitor. You inhibit the inhibitor, right? It was my most frustrating concept about all the biochemistry you learn. But you inhibit the inhibitor, right? And that allows then calcium to be reuptake into the sarcoplasmic reticulum. Now, there's a couple other ways that calcium can concentrations can be modulated, or calcium leaves the cell, right? This isn't the only way. Probably the most well-known one, because of the because it's the most well-known one, would be the sodium potassium ATPase, right? So we have our sodium, and then we have our potassium, and that's the sodium potassium ATPase. Very similar to action potentials in other cells. Most cells have them on the cell surface, and it kind of helps maintain cell membrane potential. Now, the other couple things that we want to talk about are this guy right here. So this is the sodium calcium exchanger, right? So this is responsible for taking calcium out of the cell, so Ca2 plus out, and it exchanges it for a sodium, right? So it's swapping calcium out, calcium out, calcium out. The reason that this is important is because its function is directly related to the sodium potassium ATPase. Now, why do we care about that? Because one of the drugs that they love to test you on the mechanism of action and all of the side effects, we'll go over all that stuff, is digoxin. So digoxin actually inhibits the sodium potassium ATPase, right? So really there's a decreased amount of sodium outside of the cell because this has been inhibited, right? And this is using active transport. This is just an exchanger. So this depends on concentration gradients. So if there's decreased sodium outside of the cell, you're not going to have as much calcium exchange, which means you're going to have increased calcium inside the myocardial cell, which means you're going to have a stronger contraction, right? It allows more calcium to be sucked up into the sarcoplasmic reticulum, which then leads to stronger contractions, right? And that's the mechanism of digoxin. We're really getting the effect from the calcium sodium exchanger not working, but the way that we make that not work is by inhibiting the sodium potassium ATPase. So again, inhibit that to inhibit this. And the last type of channel that we have is just a straight up calcium ATPase. So just pumping calcium out of the cell. So that is cardiac electrophysiology in a nutshell. Hope it was helpful for you, and we'll see you next time. All right, guys, I know that was another a longer one, but the concepts with electrophysiology are can get kind of intense. Hopefully you got something out of that. I know I got something out of that, just kind of reviewing all that stuff and kind of coming up with that little lesson board, I guess you would call it. Again, I am very new to making these videos. If you have any suggestions on how I can improve things or how I can make things better, just let me know in the comments. Feel free to share this if you thought it was helpful. If you didn't think it was helpful, I apologize for wasting your time. But again, I'm just doing this for myself. It's a good excuse to review this material and come up with a concise way as possible to kind of present it. So thanks for stopping by, and we'll see you next time.